moving on, we invite Aaron to come forward and share your screen. Aaron is a master's I'm sorry, PhD student in material science and engineering.
Hello, my name is Aaron Thomas. I'm a PhD student in the Junio Lab Group. Today I'll be presenting Delving into Batteries, how to look at things that violently react with air. Now, let's see where battery development might take us, why we want to know. We're all familiar with mobile devices. Your phones will last longer. We're able to make wearable sensors and things like that. Let's talk about transportation. In 2035, the European Union and several US states are actually banning all combustion engines. So car companies are working hard alongside us to make sure batteries remain safe. In addition, with certain battery thresholds, we can even start to make electric planes. Finally, in the renewable energy category, excess energy generated through solar power during daytime and wind power on windy days can be kept in large battery arrays until it's needed. Now, let's take a look. We typically see batteries with a positive and a negative end. It's good to imagine this like a cliff. Between these two sides, there's a lot of energy that's stored. Since these pieces are very reactive, any touch of air or moisture could release that pent-up energy. We want some medium in between our cliff and our ground to make sure it doesn't discharge all at once, because short circuits can lead to thermal runaway and a pretty bad day overall. What we really want to look for is the chemical reactions inside of our batteries. Besides the main reaction that will get you your energy, all of this stored energy inside these high power electrodes will leak into side reactions and make thin layers on the surface of your electrodes that we call interphases. These form naturally when you charge and discharge your battery. It's not something we build in, but they affect the performance a great deal, and they can vary a lot depending on what material you're using. If we can understand, predict, and control these delicate interphase layers, we can stabilize and produce next generation batteries. These interfaces are very delicate, however. If you try to take apart a battery to look at it, it will degrade as soon as it touches air, or even nitrogen, or even just sitting on a shelf waiting for you to look at it, it will degrade. We want to watch these layers as they form. Issue, they are very, very small. Batteries are made wrapped in thin layers around each other, as small as a tenth the width of a human hair, which you can see on the left. This small size and high reactivity makes these systems very difficult to analyze. So, how do you delve into the battery? Let's talk about how you look at things. When we want to look at something small, we have to consider the probe we're using to measure it. The one we're most used to is visible light with a wavelength of around 700 nanometers. We use this to see all the world around us. But the issue with light is that it cannot see things smaller than itself. And if we take a look at the thickness of an interphase or the thickness between two atoms, we can see it's much, much, much smaller than light. We'll need something else. Let's try to use electrons. An electron beam has an extremely small wavelength, over 300,000 times smaller than that of visible light. We can use a special battery setup that lets through an electron beam, which we still have to be careful not to let it expose to air. And we can get a video like you see here, taken by Dr. Matthew McDowell at Georgia Tech. We can watch as this silicon bubble expands as it takes on more and more and more lithium, which I think is the coolest thing ever. It's an extremely cool video. We can also see this here done by the Shirley Mung group at UCSD. We can take a look at this piece of lithium with a really thin interface. You can see the difference between this red and this blue square with just dozens of atoms worth of thickness or hundreds of atoms worth of thickness. These are very, very, very small. It's extraordinarily cool. The issue with electron microscopy is that these electron beams are very high powered. They can damage your material. They can cause other reactions you don't want. So what if we want something with a bit of a more gentle touch? Unlike an electron beam microscope or other kinds of light, an atomic force microscope uses a physical scanning tip, like a really, really sensitive record player. Because it's so small, we can actually use it to probe at these very small features we want to look for in batteries. In addition, sample prep is not nearly as strenuous, and the tool is small enough that we can put it inside a box that likes batteries much better. Here's some data that has been reported using this method. You can actually see as you cycle it back and forth, you can see these cracks form as they're being made, which I think is incredibly cool. Let's zoom in on image 6 here. What I'm trying to do here is take AFM further. I want to use all of this extra information AFM can get to try to identify, I think that this is made of more inorganics. I think this is, or maybe more organics, or I think this is really hard, or something like that. I'm trying to use all of this extra information from AFM to try to get even more information out of what we can get with these images. So thank you all very much, and thank you for attending.